Hello everyone, I'm going to be talking about our paper, Improved Bounds for Perfect Sampling of K Colorings in Graphs. I'm Shantan Chakraborty and this is joint work with Siddharth Bhandari at TIFM Mumbai. Let me introduce the problem first. The setup of the problem is that we are given a graph G with n vertices and max degree delta, and we are also given a set of colors from 1 to k, and we are going to be denoting the set of proper colorings of this graph using k colors by the set script C, and we are going to use the notation capital pi to denote the uniform distribution over this set script C. So our goal is to produce a uniformly random sample from this set script C in expected poly time in the size of the graph. Now, in general, even determining whether the set script C is empty or not is an NP-hard problem. For example, determining whether given graph is 3 colorable or not is NP-hard. The first thing is that we are going to ensure that there are enough number of colors so that the set script C for us is non-empty. So what we are going to do is we are going to be aiming for bounds like k greater than c delta, where c is greater than 1. C is a constant greater than 1. For example, whenever k is taken to be greater than delta plus 1, greedy coloring strategy just tells you that the set script C is non-empty. There is at least one coloring which is proper. Now notice that for perfect sampling, a naive accept-reject approach is not going to work, simply because the size of script C as compared to the size of the set of all colorings, proper and improper, is inverse exponential. So if you do an accept-reject sampling type of an algorithm, on expectation it's going to need exponential in the size of the graph amount of time to produce a correct sample. So our goal will be to minimize this constancy as much as possible. Now, one point that I would like to emphasize is that if you prove that an algorithm exists for k greater than, suppose, some c delta for some c, then that algorithm is also going to produce perfect samples for k's that are greater than this bound. So the real work goes into really reducing this lower bound as much as possible. And the previous best result in this line of work was by Huber in 98, who proved that whenever k is greater than delta square plus 2 delta, there exists an efficient perfect sampling algorithm. And in our current work, what we have proved is that such an algorithm exists even when k is greater than 3 delta. That is, we have reduced the quadratic dependence on delta to a linear dependence. So before going into the nitty-gritty of our algorithm, I would like to expound a little bit more on a very important sampling algorithm called Glauber dynamics, which is essentially the backbone of whatever we do here. So Glauber dynamics has been used in all sorts of settings for sampling purposes, for like sampling colorings, independent sets, matchings, all sorts of things. But in the context of colorings, here is how Glauber dynamics works. So you're given a graph, and a certain coloring on this graph. Let's call this coloring chi. And what Glauber dynamics does is it'll select a vertex v uniformly at random. So for the purpose of this example, let's say v is this vertex which is colored green. Then we will look at the set of colors k minus the colors that occupy the neighbors of v. So in this example, the colors that are occupying the neighbors of v are blue and red. Now notice that for this example, we are given k to be this set, blue, red, yellow, green and black. So the set k minus chi and v is essentially blue, green and black. So what Glauber dynamics will next do is pick a color uniformly at random from this set k minus chi and v, and let's say for this example that the algorithm picked yellow, and it's going to recolor v with yellow. And it's not very hard to see that the stationary distribution of this Markov chain is actually the uniform distribution over the set of all proper colorings. Now, let's talk about a weaker problem. That is, we don't want to produce an exactly uniform sample. We want to produce a sample which is distributed almost uniformly. That is, the distribution of our sample is close in total variation by epsilon to the uniform distribution on the set of proper colorings, where epsilon is kind of small. So the algorithm that we learn usually is that you start off from some coloring chi, and the Markov, we'll call the state of the Markov chain x naught, and we run it for some time t. That is, at every step we run one iteration of the Glauber dynamics, and if you run if you run this process long enough, one can prove that the distribution of xt will be very close to the uniform distribution on the set of proper colorings. That is the station distribution of the Glauber dynamics chain, and this t typically has a dependence of log 1 over epsilon. So technically this is called fast mixing. That is, the Glauber dynamics mixes in polytime, but this is not very good for our particular problem, perfect sampling, because this log 1 over epsilon dependence on of the time t, the running time of the algorithm, means that when you set epsilon equal to 0, this strategy essentially becomes infeasible. So before going into the particulars of our algorithm, I would like to just compare some previous work on approximate and perfect sampling. So the first result in the approximate sampling domain was given by Jerome in 95, who proved using a coupling argument that whenever k is greater than 2 delta, the Glauber dynamics is fast mixing. Subsequently, Bublé and Dyer in 97 substantially simplified Jerome's analysis by introducing a new technique called path coupling. And a major breakthrough was in the year 2000 by Eric Vigoda, who showed that whenever k is greater than 11 by 6 delta, one can show the existence of an algorithm which produces an approximate sample in polytime in the size of the problem. And in the year 2019, Chen, Delcourt, Moitrov, Perarnau, and Possel proved that using Vigoda's technique at least, you cannot do much better, and you can at most reduce this dependence by some constant factor where the constant is really small. In comparison, not much work has been done in the perfect sampling domain. So, as I've mentioned before, the first breakthrough was by Huber in 98, who proved this quadratic bound, quadratic in delta. And last year, Feng, Guo, and Yin in 19 proved that perfect sampling algorithm exists whenever k is greater than delta square minus delta plus 2, and k is like order log n. But this still is kind of unsatisfactory because the quadratic dependence remains. A remarkable result by Liu, Sinclair, and Srivastav again in 19 showed the existence of a deterministic approximate counter for the set of proper colorings whenever k is greater than 2 delta. And using a connection with a very old, very celebrated paper of Jerome Valiant and Vazirani, one can show that deterministic approximate counter implies a perfect sampler. But the problem is that this reduction will give you a running time of the perfect sampling algorithm, which is something like n to the power delta. So delta needs to be order 1 for this reduction to work. So this left a lacuna in the literature, and our work addresses this lacuna, where we show that even linear dependence on delta works out, and even in that domain there does exist polytime algorithm which produces a perfect sample. And the most important thing is that this breaks the quadratic barrier for general graphs which had remained for so long. So now we are going to start to explain the main framework on which all or most perfect sampling algorithms are based, which is CFTP. So we ask the question that given a Markov chain P with a station distribution pi, and I'm overloading notation here a little bit, can we produce an exact sample from this distribution pi? Now this might seem to be a very outlandish question to ask at first, but this was answered in the affirmative by Prop and Wilson in '96 in a breakthrough paper where they introduced the coupling from the past framework, which we will abbreviate as CFTP. So I'm going to briefly explain how the CFTP algorithm works and not go into the proof so much right now, but we'll see that briefly later on in some later slide. So the CFTP algorithm works like this. Suppose these bags here, these bags are essentially this is essentially the state space of the Markov chain, and these blue points are the members of the state space of the Markov chain P. And for this, what the CFTP algorithm does is it will generate random updates u-1, u-2, u-3, where each of these u's is a random update function mapping going from state space to state space, and these indices are negative time indices, in the sense that from some negative time, say minus t, will generate t of these random update functions from minus t to minus 1. So u-1, u-2, u-3 up to say some u-t. Now how the algorithm works is we'll start off at some time, say small t equal to minus I, and we will apply this update function u of minus I to every state in the state space of the Markov chain, and we will keep track of the image of u of minus I. So once we apply u of minus I to the entire state space, let's say these bunch of 4 or so states is the image of u of minus I. Then in the next stage of the algorithm, we are going to apply u of minus I plus 1 to only these 4 states, and keep track of the image of u of minus I plus 1, which might be a smaller subset or a subset of equal size. And we continue this process until time t equal to 0. Now at time t equal to 0, we will check whether the size of the image of all these updates, that is from u of minus I composed u of minus I plus 1 composed up to u of minus 1, if the size of this huge long sequence of updates is 1. If it is 1, let's say then whatever state these updates are coalesced to, we will output that as output of the algorithm. If not, what we will do is we will go back in time further, maybe generate some new random updates, and start at time time that is further back in time. So and we keep doing this. So once at time minus t, we'll start this process again. So we apply u of minus capital T to the entire state space and look at its image, and then apply u of minus capital T plus 1 to only the points inside this image, and so on and so forth, until we get to u of minus I. But notice that when we get to this time t equal to minus I, we'll be reusing the update functions that we had sampled previously. So we do not discard these random functions that we had sampled before, and this is how the algorithm progresses. We go up to time t equal to 0, check whether the size of the image of the sequence of updates is 1. If yes, then output the sample. If not, then go back in time, maybe generate some extra updates, and keep reusing the updates that have already, the update functions that have already been sampled. So this is exactly what is you can say written in the text. And the claim is that if one is guaranteed that coalescence will happen in finite time almost surely, then whatever uh, that is this minus t time for which coalescence happens is finite almost surely, then if the output of the algorithm is omega star, then this omega star is actually distributed exactly according to the stationary distribution pi. Now let's take a small example again. As you can see that the first iteration of the algorithm, say we start at minus I, and this orange ball are the states where u of minus I is applied, and it maps to the smaller orange ball, and then we apply u of minus I plus 1 to the smaller orange ball, which maps to again another smaller orange ball, and so on and so on. But in this first iteration, we see that the sequence of updates does not coalesce to a single density. It coalesces to this orange ball with 3 members in it. So what we do is we go back to say time, we do several iterations, and we go back to say time minus t. And again we start with all possible states where we apply the update function u minus t to all these guys. And we'll look at its image, which is this smaller green ball now. This iteration being highlighted by the color green. And we go forward, and once we reach minus I, we are going to be reusing the update functions u minus I, then subsequently u minus I plus 1. And as we follow the green balls, we see that the algorithm has terminated at a green ball which has a singleton element, and that is omega star, and that is exactly what we output. This is how the algorithm works essentially. So one thing to notice is that suppose the algorithm ran from some time minus I plus 1, and coalescence did not happen, and we went back and for one more iteration from time minus I, then the image of the update, this second iteration, is actually a subset of the image of the first iteration. And you can see this very clearly in the example, in that the first iteration, the image of the first iteration, which is the orange bag, is actually a superset of the image of the final iteration, which is the green bag. So let's move on. I think a better way to demonstrate CFTP is via an example, a simple accessible example. And the example that we are going to consider is a very simple random walk on the integers 1 to 5, and in general 1 to n. So what we do is how the CFTP algorithm will work here is that we'll consider the state space of this Markov chain, which is just the elements 1 to 5, quite literally these 5 blue points. And we need to specify update functions for each of these negative times. And for this Markov chain, the update functions are quite simple. They are these random variables, tau minus 1, tau minus 2, up to tau t for some t, which are uniformly randomly sampled from the interval 0, 1, and they are independent across time. Now what happens is, suppose at say time minus I, one has to apply an update function, that is u minus I, to the state j. So what happens is, if this tau t, that is tau minus I, is greater than half, then we update j to j prime, which becomes j plus 1, and if not, then j prime is set to be j minus 1. And we do this process for all members in the state space, as I had mentioned before. And what we do is, suppose we start at minus 1, then again go up to 0 and see that things have not coalesced. Then we go back to minus t, again start from all states 1, 2, 3, 4, 5, and keep on applying the update functions u minus t, and then reuse the update functions that we had sampled before, that is, reuse these taus that had been sampled for minus I plus 1 and so on, and we observed that coalescence happened at this state j star, and we simply output j star, and what Proper-Wilson proved is that this j star is actually distributed according to the stationary distribution of this Markov chain, which is essentially uniform on 1 to 5. So some more comments. Notice that for each single element in the state space, its marginal obeys the correct distribution. That is, for each member in the state space, let's take this example of omega of minus I at time minus I. The evolution of omega minus I is as if we started a chain at omega minus I and kept on applying the Markov chain, the update operation P to it until time minus 1. And essentially we evolve all the states according to the same update rule, and this in the literature is called a Grant coupling. And we think it's essentially a joint evolution of all the Markov chains together, and when the algorithm terminates, what we see is that all the chains have coalesced to this single state. In this case, what we have shown to be omega naught, previously what we called omega star. So regarding so that's all about the CFTP algorithm. But regarding the proof, the intuition is something like this: ki, suppose someone asks me ki, why are we going back in time? Why are we not evolve? Why do we not start from every state and evolve forward in time until all states have coalesced? So the point is that the definition of the stopping time, stopping time that we define as when all states coalesce, can bias the distribution of the sample that is output by the algorithm, and we do not want this bias, and there are counter examples to that effect also. So essentially we want to remove the bias that is brought about by this stopping time. So what one is guaranteed is that if one evolves joint chain, that is chains from every state forward in time and goes up till infinity, then all the chains will have coalesced with probability 1, and the distribution of the state at time infinity will be exactly according to the stationary distribution pi. Now obviously this is infeasible algorithmically. So intuitively what the CFTP algorithm says is that you shift the indices by minus infinity somehow. That is, you pull down infinity to 0 and 0 to minus infinity, and you pretend as if you have been evolving chains from all the states at minus infinity until time 0, and you output at time 0, so that you're guaranteed that the sample you output is actually distributed according to the correct distribution. Now mathematically this does not make any sense, and if I had to be very precise, what I would say is that the definitions of these stopping times, that is this stopping time minus t, which we define as the first time, such that if one evolves chains from every state in a joint manner, such that at time 0 there is coalescence, the definition of this stopping time is different from the definition of the other stopping time when we were evolving it forward and observing coalescence. The distribution of these two times are the same, but these two stopping times actually behave very differently, because if you once coalescence, like by the very definition of this stopping time minus t, once coalescence has happened, if we go further back in time, like suppose we evolved all chains from time minus capital T and coalescence happened 0, and we went further back in time, uh, by the very nature of our updates, by reusing the random functions, we ensure that this is not going to change the output of the algorithm. So essentially what this means, that if you take the limit of this stopping time t to infinity, the distribution of this random variable x minus infinity is almost surely the the distribution of x infinity, which is just this pi. So that is a very rough and very rough proof of the correctness of the CFTP algorithm. And if you did not understand it, please forget about it. And this is a complicated algorithm, so that is why this wet flow sign is here, as in there are many subtle things that one needs to take care of, but we are not going to dwell on this much longer. So the point is that the crux of the algorithm is that one needs to ensure that the stopping time t is finite almost surely, and for efficiency one needs to ensure that the expectation of the stopping time t is polynomial in the size of the problem. And yeah, that is so. Okay, so now we are going to move on to CFTP for colorings, and let's see some of the issues that can occur. So again, for CFTP for colorings, what do we need to specify? We need to specify the update function. So our state space is just all proper colorings, as you can see. But how do we specify the update functions? So each update function will be two tuple, one permutation on the set of all colors, and which is again uniformly randomly chosen, of course, and one vertex v on the graph, which is also uniformly randomly chosen. And what we do is that at any time in the evolution of the algorithm, given some coloring, some proper coloring, we look at the vertex that is given to us by the update function. In this case, let's say vi, and we look at the first color in sigma that is not in the neighborhood of vi. So in this example, the colors that occupy the neighborhood of vi are blue and red, and so the first color in sigma that does not occur in this neighborhood is yellow, and we simply recolor yellow. And it is not very hard to see by the experiment that we pick each of these sigmas independently across time, and we pick each of these vi's independently across time. It's not hard to see that this is essentially the global dynamics. For each coloring, we are just doing a global dynamics. It is just that we have coupled the evolution of all these states together, because we are using the same update function at a single time. So yeah, so what are the issues? The issues are that now one has to somehow keep track of the images of each update function, and that is hard because the cardinality of this set of proper colorings is exponential in n. So that is where most of the work in the algorithms goes, that one has to somehow keep track in an efficient manner of all the colorings. And another issue is that what is the expected running time of this algorithm? Now, why did we not face this problem in our toy example? The clear-cut answer is there is an ordering on the state space. So since say like 5 is greater than 1, and our update functions, if you notice, preserve this ordering. That is, if the integer L is less than the integer J, then at time T, the update UT will preserve the order between L and J. And so instead of keeping track of all of these guys, one can just keep track of the minimal and the maximal element, or rather the minimum and the maximum element in this case. And whenever these two coalesce to the same state, we can just output that state and be done. But this is not something that we see in colorings, because there is no natural ordering on the set of colorings. And yeah, this is mainly the problem that we address in our paper. Yeah, so now we'll start to describe the idea with which Huber tackled the issue of keeping track of an exponential number of colorings, and that idea is bounding chains. So this idea appeared independently in two papers, in 98 in Huber's original paper, and in 99 in a paper by Hagstrom and Nylander. And what is a bounding chain? It is actually a Markov chain on the state space 2 to the k to the v. That is, at any time t, the bounding chain at any vertex v assigns a list of colors instead of a single color. Maybe a single color also, that is also valid, but in general, BCTV is a list of colors. So before going into the details, let me just go over some salient features of the bounding chains. So suppose we want to check at time 0 whether the image of the sequence of updates is a singleton. The bounding chain can actually do this efficiently without any false positives. And Huber proved that for large k and for t of the order of delta times n log n, the probability that the image of the sequence of updates from time minus t to minus 1 is actually singleton is strictly greater than half. That is, on expectation, only 2 iterations of the CFTP algorithm will produce a singleton which is correctly distributed. So what is the idea behind the bounding chain? The idea is to maintain this invariant. Now, what is the invariant? The invariant is that suppose we have evolved the chain from time minus t to time t. That is, we have applied the updates up to time t minus 1. Remember that this t is negative. So, and let's say that at this point of time, the image of the sequence of updates has some chi1, chi2, some number of proper colorings. That maybe it is as large as the entire set of proper colorings, maybe it is smaller, but it has some number of proper colorings. And the idea is that consider any vertex, let's say this vertex at that time t, then the list assigned by the bounding chain at that time t to this vertex will contain all colors that any coloring in the image of this sequence of updates assigns to this vertex. So let's take a very small example. Let's say there are 2 colorings in the image, chi1 and chi2, and chi1 assigns the color red to this vertex, and chi2 assigns the color green to this vertex. Then the bounding chain will assign a list to this vertex that contains both colors and maybe more. So this is the invariant that we need to maintain throughout the evolution of the bounding chain. In other words, the bounding chain acts as an upper bound to all the possible colorings that may be in the image of our sequence of updates. Now this is clearly efficient, because the bounding chain is a polynomial size structure, but it contains the information of all possible colorings and quite possibly an exponential number of colorings that may exist in the image of the sequence of updates at the time t. And how do we check that the image, after applying updates from -t to -1, how do we check that the image is a singleton? We simply look at the list sizes that the bounding chain assigns to each of these vertices, and if for each vertex the list size is 1, then we know that by the invariant we can claim that the image of the sequence of updates is indeed a single color array. So recall that how did we design the CFTP, the not inefficient CFTP for colorings, is that our update functions at every point of time was a two tuple. The first coordinate in the tuple was a uniformly randomly chosen permutation on the set of all colorings, and the second component was a uniformly randomly chosen vertex. And at time t, we updated the color at this vertex by the first color in sigma that did not appear in the neighborhood of v. So this is just a reminder. So Huber's algorithm actually progresses in two stages. The first stage is called the warm-up phase, which goes on for time n log n, and the second stage is what we call the coalescence phase, which goes on for time delta times n log n. So I'll be explaining the warm-up phase first. So essentially, how does the chain start? At time minus t, at the very beginning of the algorithm, what it does is that the bounding chain assigns the entire list of colors, in this case 5 colors, red, yellow, blue, green and black, to every vertex. And this trivially ensures that this bounding chain indeed maintains the invariant property that the bounding chain acts as an upper bound to every coloring in the current image. Okay. Then the evolution of the bounding chain during the warm-up phase progresses like this. Suppose there is some -i index which is inside the warm-up phase, then the algorithm is updating the vertex v. Then in the warm-up phase, what the algorithm will do is simply look at v, look at sigma -i, and assign the first delta plus 1 colors of sigma -i to this vertex v as its list. So for this particular graph, delta is 3, max degree is 3, so delta plus 1 is 4. So as you can see, if sigma -i is black, yellow, blue, red and green, then the algorithm assigns the list black, yellow, blue and red to the vertex v. So this process of blindly assigning delta plus 1 colors delta plus 1 colors to each vertex as its list goes on for time n log n. So by the coupon collector problem, we know that at the end of this phase, by high probability, almost all of the vertices, or rather with high probability all of the vertices, have a list size of delta plus 1. And clearly the invariant is maintained, because at every step, how do we, if you were to update a single coloring, recall that we simply looked at the first color in sigma -i that was not in the neighborhood of chi. Now the point is that since the max degree is delta, this first color that does not occur in the neighborhood of v will definitely show up in the delta plus 1 size list that we have assigned at v. So this ensures that the invariant, that all the colorings in the image up till that time are actually contained in the bounding chain at that time. So this is essentially what is written here. So at least up till the warm-up phase, this very important invariant is maintained without fail. Yeah. So this is the example that at the first color that does not appear in the neighborhood of V, which is black, appears in the delta plus 1 size list or 4 size list in this case that we have assigned at V. So at the end of the warm-up phase, as I said before, with high probability, all of the vertices have a list of size delta plus 1. So okay, now we'll be dealing with the coalescence phase. So to talk about the coalescence phase, we will need to address we'll need some definitions. So suppose again consider a vertex V and consider its neighborhood and the lists assigned by the bounding chain to the vertices in the neighborhood of V, and consider the union of these lists. So for example, in this the neighborhood of V in this example, if you take the union of the lists assigned to the neighbors of V, that union will result in red, yellow, blue and green. That is what we have shown in this diagram, and there is only one color outside this union, that is black. This union of the lists of the neighbors of V we will call STV. Sorry, there's a typo here, it should be V. And and as you can see, this STV set is a subset of the colors K, the entire list of colors K. But this STV is definitely also a superset of all blocked colors. That is, since we have been maintaining the invariant, any proper coloring, any colors that a proper coloring might have assigned to these neighboring vertices, whenever that proper coloring is in the image of our sequence of updates, will show up in the list of these neighbors. So for example, in this particular iteration of the bounding chain algorithm, all the image of the updates till this point of time will only contain proper colorings that assign red to this vertex. This is easy to see because we have because of our invariant. Okay. So what happens in the coalescence phase? So we have two cases. The first case is that suppose at time t, where t is within this coalescence phase, where t is within this coalescence phase, we look at again, suppose we are updating V, we look at sigma and we look at the first color in sigma. So suppose the first color in sigma is a color that is outside STV. That is, in this example, the only such color is black. So the first color, if the first color in sigma is black, then we simply update the list of at V with the single color black, and that's it. And we have made progress. I mean, this is definitely progress. The bad cases when the first color is not a color that is outside STV. In that case, we just give up and assign the first delta plus 1 colors of sigma as the list at V. So in this case, let's say sigma t did not have black as its first color, but instead had red, and red lies inside STV as we have seen before. So we will assign the list red, green, black and yellow as the list at V. One can show using a similar argument that we used for the warm-up phase also, that the invariant that all the colorings in the image of the updates till now are actually contained in the bounding chain at this time t. And one can actually see that case A will be favored more if K is large, because with very high probability in that case, um, the color in the first color in sigma t will lie outside STV, but that only happens if K is large. But if K is small, then definitely case B is favored more, because there are only very few colors outside STV, as you can see in this particular case. There is only one case where this the first color is actually outside STV, and that case is only when black comes in the first place. So this is what happens in the coalescence phase. And uh, if you consider this definition, or WT, of all the vertices at time t, again recall that t is negative, all the vertices at time t, such that the list at these vertices is a singleton. What we want to show is that at time zero, the size of this set is actually n. That is, the list size at every vertex has reduced to 1. Now, if you a little pondering will tell you that this mod WT, the size of the set WT, is actually performing a random walk on the set 0, 1 to n, with 0 as a reflecting state and n as an absorbing state. And what Huber showed in his paper is that if k is greater than delta square plus 2 delta, then with the warm-up phase being n log n long, and the coalescence phase being delta times n log n long, the probability that the size of W naught will be n is strictly greater than half. But in fact, scrutiny of Huber's analysis will tell us that actually k need not be greater than this worst case bound delta square plus 2 delta. This is very much a worst case bound. K simply needs to be greater than the maximum list size during the coalescence phase over all vertices times delta plus delta. And this is essentially what we exploit in our algorithm. We show using a new kind of coupling that this max list size during the coalescence phase can be actually maintained at 2 instead of the worst case bound of delta delta plus 1. Yeah. So finally, I'm going to start describing our algorithm and what we do differently so that we get the improvement in the lower bound. So our algorithm also runs in two phases. The first is the warm-up phase, and the other one is the coalescence phase. The warm-up phase lasts around n delta steps, order n delta steps, and the coalescence phase lasts around delta times n log n steps. So a very nice feature of our algorithm is that at the end of the warm-up phase, the bounding chain, the sizes of the lists that the bounding chain assigns at every vertex are all at most of size 2 with probability 1. Now recall that in the coalescence phase, this set WT of vertices which have lists of size 1, this quantity, the size of the WT, it performs a random walk on 0, 1 up to n, with 0 as a reflecting state and n as the absorbing state. And what another feature of our algorithm, what it ensures is that the maximum size of the lists even during the coalescence phase is 2. So for a positive drift, what we need to show is that if you recall from the previous slide, that if k is greater than max list size during coalescence phase times delta plus delta, then we have a positive drift. And in our case, since during the coalescence phase the max list size at any vertex is 2, This gives us the bound of 3 delta. So the main idea is changing the underlying CFTP process, that is changing the coupling, so that the uncertainty at any vertex, the uncertainty about the number of colors that can be present at any vertex is reduced to a very large extent. So to describe the algorithm, before going into the full description of the phases, I'm going to describe two primitives, two types of updates that we have. One is the compress update and the other is the contract update. So these UIs, they can be of two types, compress and contract. And I'm first going to describe what these are and then move on to how we use them in the phases. So first going to describe the contract updates. So the main idea underlying all of our algorithms is something called bias sampling. So what is this? So our goal here, when I'm describing the contract updates, I'm assuming that the bounding chain is in such a position such that if suppose I'm updating the list at the vertex V, the neighbors of the vertex V have list sizes of at most size 2. Why is this justified? We'll see that later, but bear with me for now when I say that we will ensure that our chain, our bounding chain, reaches this kind of a very nice state after a certain amount of time, that is essentially after the warm-up phase. Now the point is that okay, so we have ensured that the neighbors of V have list sizes at most 2, but how do we maintain this condition? That is, how do we maintain that V also has a list size of 2, or that any vertex that is being updated, given this nice condition that we just assumed, maintains a list size of 2, or rather at most 2. So that is where these contract updates come in, and the idea behind them, behind this kind of an update, is bias sampling. So yeah. So let's take a very generic example. So what I want to do is, I want the bounding chain to produce a list of 2 colors, say C1 and C2, and given any coloring chi which is in the image of the updates till that point of time, I want to be able to update chi so that our invariant, where the bounding chain upper bounds chi, is still maintained. So how do we do this even when the list size becomes so small, is what the contract update is all about. So what I want to simulate essentially is, if the bounding chain produces a list of size 2, that is of 2 colors, say C1 and C2, and if I provide this list to chi, how can chi couple itself to the bounding chain and use this C1 and C2, use these 2 colors C1 and C2, so that the evolution of chi looks like a Glauber dynamics. What I mean by that is, the evolution of chi, it should look like chi has picked one of the colors C1 or C2 as if from the uniform distribution over the set S minus T. Now what is this T? This T is essentially chi of n of V. That is the set of blocked colors at the vertex V. So, but for brevity of notation, I've used this notation T instead of the rather heavy chi of n of V. So I hope this is clear. So I'm going to say it again. My goal is, given a list of size 2, say C1 or C2, I want to be able to update chi, the coloring chi, at V, at some vertex V, such that it seems as if whatever color chi chooses, either C1 or C2, it seems as if chi has been updated according to the Glauber dynamics. That is, the whatever color chi chooses has been picked from the uniform distribution over the set S minus T. So how do we do this? So chi is provided this list C1 and C2, and chi tosses a p biased coin. So yeah, so if okay, so first of all, what are C1 and C2? So C1 is a color that the bounding chain chooses uniformly at random from the set K, that is this outer black set, the large set, the set of all colors, minus S. Now the bounding chain has access to S, that is the union of the lists of the neighbors of V, and so the bounding chain can choose this color C1 from the set K minus S uniformly at random. And the second color C2, the bounding chain samples uniformly at random from the set S. So one color is sampled UAR from outside of S, and one color is sampled UAR from inside of S. And this is what C1 and C2 are. So there are two cases. One is when C2 is outside of the blocked set T, and one is when C2 is inside the blocked set T. But of course the bounding chain does not know what T is, so it can't do anything about that. The bounding chain just samples these two colors C1 and C2 and hands them to chi. So what chi does is chi will toss a p biased coin, and if heads comes up, chi will just recolor V with the color C1. If tails comes up, then chi will not use C1 and it will look to C2. Now the problem is that if C2 is outside the block set, then chi can definitely use it. It's a bona fide possible color. But if C2 is inside the blocked set, then chi will not be able to recolor V using C2, because C2 is occupying some neighbor of V. So in the first case, chi will just color V with C2, but in the second case, chi has no other choice. It will discard C2 and it will just recolor the vertex V with the color C1. Now why did we do all this? We did all this this idea of bias sampling, so that it seems as if chi is picking a color uniformly at random from the set K minus T, right? So, and if you just put these words into an equation, you'll find that the p bias, the probability p, the bias p, must satisfy this equation. And solving for p, we find that if k is greater than the size of S plus the size of t, then p is in fact a bona fide probability. That is, p lies between 0 and 1. Yeah. So now a very basic question that I forgot to mention at the beginning is that why can't we just simply assign C1? Why go to C2 in the first place? But if we do that, we'll not be assigning any mass to this annular region here, the annual region S minus T. So that's why we need to sample two colors, and we can't just get away with sampling one. Yeah. So we coming back. So we ensure that k is large enough. We ensure this condition by picking a k which is greater than size of S plus delta, because this set of blocked colors is at most delta being the max degree of the graph. Now the point is that remember at the very beginning I had assumed that this S whenever we are doing a contract update, we assume that the neighbors of the vertex V, the vertex being updated, have list sizes at most 2. So this S can be at most 2 delta, and that is how that is one way to see that we are getting a bound of k greater than 3 delta. So yeah, moving on. let's take a concrete example. So let's consider updating this sky at this green vertex u. So the contract updates will be of the type sigma tau u, where u is the vertex to be updated, tau is a random number between 0 and 1, and sigma is permutation on the set of colors, sorry, picked uniformly at random. So essentially what chi does is what I just described earlier. Uh, in this case, we see that C2 is actually outside the block set. So what chi will do is it'll check whether this tau, this number provided to it, is less than p, and this p is what we computed earlier, and this p is unique to this chi, by the way. So for every different chi in the image of our sequence of updates, this p will be different. So it should actually be p sub chi, but whatever. So this chi will check whether tau is actually less than p. If yes, then u will be recolored C1, that is black. And if no, in this particular case, u would have been recolored green, but as you can see in this case, it came out to be heads. So this vertex was recolored black. So anyway, let's move on. This is not quite correct. This entire what we did just now. So it is indeed true that this bias sampling allows us to just provide a list of size 2 to chi and make it look as if chi is speaking uniformly at random from the set k minus t, but there's something wrong with the bounding chain itself. So the point is that we are able to maintain the invariant, that the bounding chain upper bounds any chi in the image of the updates till now, but the bounding chain does not have any drift to the as in the quantity size of wt does not have any drift towards n. This is because from what we did earlier, the bounding chain always produces a list of size 2, and we must take care of this somehow. Otherwise, what will happen is the bounding none of the lists will ever go down to 1. So we need a non-trivial probability of the bounding chain assigning a list of size 1 at the vertex v. So one way would have been to do this would have been if the bounding chain knew exactly what this value of p was, but as you can see, this p is a function of this t, right? The block set, that is chi and v, and of course the bounding chain has no way of knowing what this t is. So yeah, so that can't be done. Basically, if the bounding chain knew the value of p, it would toss the p biased coin itself and pass the value down to the ghost down to the underlying the chain chi, and chi would accept and reject based on that coin toss. But of course, the bounding chain does not know what this value is, and it can't toss the coin for the underlying chi. So what can we do? What we do is we underestimate this probability p, in the sense that we come up with a coin PBC which is smaller in bias than this coin which is p whenever p comes up heads. So yeah, sorry, whenever PBC comes up heads, P definitely comes up heads, but there are some cases when PBC comes up tails, but P can even in those situations come up heads. That is essentially, in technical terms, we are going to monotonically couple P and PBC. But the point is, since we are underestimating this value of P, we can simply replace this size of tau, this size of t or chi and v rather, with delta. And this is something, this value is something that the bounding chain has access to, because the bounding chain knows exactly what the size of the set STV is, and the bounding chain can simulate this coin. So essentially, then the algorithm boils down to this, that the bounding chain, when it is updating u or v or whatever, let's say when it is updating u, the bounding chain will pick a color C1 at first outside of the set S. In this example, there are two colors, yellow and black, and the bounding chain will toss the coin PBC, and I've used P prime instead of PBC here to make it look less cumbersome. So the bounding chain tosses the coin PBC, and if it comes up heads, the bounding chain simply does not sample C2 at all. It recolors U with the color C1, in this case black, and it just hands over this color C1 to the underlying chain chi, and chi can happily recolor U with this color black as well, because the coins are monotonically coupled and the marginals are fine. But if this coin P prime comes up tails, then the bounding chain has nothing else that it can do. It essentially has to sample C2, form the list, two-size list C1 and C2, and pass that list down to the coloring chi for it to update. So yeah, so these are the contract type of updates, and again I'm going to remind you that what the contract type of updates do is essentially once every list, the list of every vertex has come down to a size 2, the contract updates first of all ensure that all the list sizes remain at most 2, and also that the bounding chain has a drift, sorry, not the bounding chain, the quantity, the size of the set WT has a positive drift towards N. So yeah. So next, I'm going to describe the compress type of updates. So the compress updates are slightly different from the contract updates, in the sense that in this case we won't be looking to reduce the list sizes to 1 or 2 or anything like that. We simply we want something else from the contract updates. What we want is that if suppose we update two neighboring vertices using a contract update, then what we want is that the lists of these two vertices should have a very large intersection. In fact, what we will see right now is that after the consecutive compress update on two neighbors, the lists assigned at those two neighbors will have intersection delta, as in they will have delta colors in common. So why do we want to do such a thing? So essentially the point is that the compress updates, suppose we have updated all the neighbors of a vertex B using the compress update, then all these neighbors, the lists of all these neighbors have intersection of size delta, that is they have delta colors in common. What that means is the union of the lists of the neighbors of that vertex is of size at most 2 delta. So this is a very nice condition for us. This is essentially the condition that we require to run the contract updates, and that's the main motivation behind coming up with this compressed kind of an update. So the update is actually very simple. We will fix a set A priori, an arbitrary set of colors A of size delta, and for the suppose we are updating at the vertex U, what we will do is pick a color C1 uniformly at random from the set k minus a, and the new list that the bounding chain will assign at u will be this set a union with this color c1. That's it. That's as far as the bounding chain is concerned, that's all it needs to know. But again, the question comes that how do we maintain the invariant that for any coloring chi in the image of the updates till now, how is it that the bounding chain upper bounds all these chi's? So as you can see, the compressed updates are of the form a c tau u, where again a is the set a, c is the sorry, this is a typo, this should have been c1. c1 is a color picked uniformly at random from the set k minus a. Tau is a real number picked UAR between 0 and 1, and u is the vertex where the update is happening. So okay, so now we'll see how exactly any chi in the image of updates till the time t is a member of essentially belongs to the bounding chain. That is, at any vertex v, chi of v or rather chi prime of v will belong to the set bc t of v or u. Yeah. So what the bounding chain does, so what does the bounding chain have access to? The bounding chain has access to the set a and the color c1, and it just yeah. But for a chi which is in the image, what the chi does is initially this chi will pick a color c2 uniformly at random from the set a minus chi nv. So looking at the picture, we see that there can be actually two cases. So this c2 will always be outside the block set. So the block set here is shown by the orange boundary, and the c2, of course, by its very definition, will always be outside this block set. c1 on the other hand can be inside or outside the block set. c1 was sampled, if you recall, c1 was sampled from the set k minus a. So c1 will be outside this fixed set a, in this case green, red and black, but c1 can definitely fall inside the block set because the bounding chain has no idea what the block set looks like. So one good case is when the set a is actually equal to the block set, that is chi nv, and we are lucky in this case because then it automatically means that this c2 is actually picked from the exact from the correct distribution. That is, c2 is picked from the set k minus chi nv. So the chi can just recolor u with c2 in that case. But what if that does not happen? So yeah, and that's a non-trivial case. So case 1 is when c1 is actually inside the block set. Okay, case 1 is when c1 is inside the block set, and chi just simply cannot use c1 because c1 is blocked. So chi is forced to use c2, and it just recolors u with the color c2. But case 2 is when c1 is outside the block set. So chi has a chance of using either c1 or c2. Now recall that we must make sure that whatever color chi chooses to recolor u with, the choice of color must seem like it has been picked uniformly at random from the set k minus chi nu, right? So to ensure that, we are again going to use the idea of bias sampling. So in this case, when Kai has a choice between C1 and C2, Kai will again flip a coin with bias P, and if it turns out heads, then Kai will recolor U with the color C2, in this case black, and if tails, Kai will recolor U with the color C1. And again, using the same sort of idea, the same sort of equation that we had in the case for the contract updates, one can show that a P does exist for K large enough such that chi prime U is actually distributed uniformly, looks like it's distributed uniformly at random on the set K minus chi and U. So these are the two types of updates. Now let's move on to the actual meat of the thing, the how the chain works. So first I'll describe the warm-up phase, where our focus will be to bring down the list sizes of every vertex to at most 2. So we start off as we did in Huber's algorithm, that at time minus t, the bounding chain assigns full lists, that is k size lists, in this case 5 size lists, to every vertex. And what we'll do is we will sequentially update the neighbors of U1 with a compress update. So our focus, remember, will be to bring down the size, the list of U1 to size 2. In fact, we have to do this for every vertex, but as a demonstration, let's just see how we can do it for U1. So recall that when I started describing the compress updates, I said that why we do a compress kind of update is that whatever vertex, the list, the vertex for which we want to bring down the list size to 2 will first update its neighbors, because if we use a compress kind of update on the neighbors of U1, then that is U2, U4 and U3, then the intersection of the lists of U2, U4 and U3 after a compress update will be of size delta, in this case 3. So after 3 compress updates at U2, U3 and U4, the union of the lists at these 3 vertices will have at most 6 colors. Now our example is erroneous, because this is only 5 colors, but one can imagine that there are more colors that are actually there that are not in the diagram. And forgive me, but please do that in your heads. Imagine that there are something like 9 colors. So then at U1 we have 3 colors that are not captured by the union of the list of U2, U4 and U3. So after this happens, one can immediately apply the contract update, because the condition that k is greater than 3 delta, that is k is greater than 9, is satisfied. Sorry, we actually need 10 colors then, my mistake. So the condition that k is greater than 3 delta is satisfied, and that falls immediately in the ballpark of the contract update. And so at U1 we apply the contract update, and the list size at U1 goes down to 2. Now how do we do this for every vertex? That is slightly cumbersome, but let me give you a simplified version. So suppose instead of aiming for k greater than 3 delta, we were aiming for k greater than 4 delta. And what you essentially do is put an ordering on the vertices v1 to vn, and apply a compress update on each of these vertices v1 to vn. And then you come back to v1 for another pass, and sequentially apply a contract update to each of v1 to vn. And a moment's thought will tell you that if k is greater than 4 delta, essentially at every vertex, the condition that k needs to be greater than s plus delta for the contract update to be applied is satisfied, and hence at every vertex we can get the list size down to 2 if k is greater than 4 delta using this technique. I'm sorry. With a little more work, which is a little cumbersome, so we will not cover that in this presentation, but it's not much of a stretch from here. One can show that actually even with 3 delta with some clever updating scheme, clever ordering rather, in clever order in which we update, one can actually make this work for 3 delta as well. And yeah, so yeah. So after the warm up has happened, which takes about order n delta time, we have ensured the condition that at every vertex the list size is at most 2. So now we go into the coalescence phase, where we will start applying the contract updates, because contract updates can be done now because k is indeed greater than s, which is at most 2 delta, plus delta, which is 3 delta. And since we have taken k greater than 3 delta, at every vertex we can indeed apply the contract update. And one can show that, yeah, so one can show that if this contract update is applied time and time again, uh, uh, and if the vertex, say ut, is being updated at the time t, then the probability that the bounding chain assigns a list of size 1 at this vertex ut is strictly greater than 0. And what this means is that if one follows a similar kind of analysis, that a drift analysis that we did for Huber's bounding chain as well, one can show that if this coalescence phase lasts for time, say some order delta times n log n, then the probability that at the end of the coalescence phase, the list size of every vertex v in the graph has dropped to size 1 is strictly greater than half. So, and this is essentially what we wanted, because now we can simply repeat this argument that in expected 2 iterations of the CFTP algorithm, the algorithm will terminate and output coloring, which is which seems like it has been sampled uniformly at random from the set of all colorings. And that's it for our algorithm. Now before concluding, I want to move on to some open questions. So the most natural question is, can we push this bound down to 2 delta? Now why 2 delta? Because 2 delta seems to be a very natural bound that comes out from the path coupling arguments that can be found in the approximate sampling literature. And the honest answer is we don't quite know. Our techniques have not been able to push 3 delta down to 2 delta, but one good news is that there do exist coupled evolutions or random functions which do coalesce quickly, as in polynomial time, for k greater than 2 delta. And this is not a very difficult argument, as if you think about it, it's not very hard. As in suppose there is one chain x naught that you evolve for some amount of time, and then for every other state chi in the state space, you simply couple the individual evolutions of all chi's with the initial evolution of the chi naught, and one can show that with high probability in polynomial time, this kind of a coupled evolution will lead to all the chains running from all states to coalesce to a single state. But the issue is that we don't have a bounding chain to keep track of all these states. And we have been thinking about this for some time, but as of now, we don't seem to have a bounding chain to capture this coupling, or to track the behavior of this coupling. So before concluding, I just want to flash some pictures of us. So this is me, and this is Siddharth, looking as serious as usual. Thank you for your time.